Okay, welcome back. And we have one more lecture, so bear with us. We're gonna finish early today. I mean, not early, earlier than yesterday. We're gonna finish about 12 something. And we have the lunch until 1, then we continue with the hands-on. But before that, we have 1.5 hour lecture from Lucivan, from Thermo Fisher, who've been supporting us to do this workshop and to acquire the technology. And as I heard just a few minutes ago, they will support us to get a big discount to buy the face cutter, the die cutter for the low moisture. So let's give them a big hand.
Yay! All right, everybody, good morning. I think I've met everybody already, but a formal introduction. I'm Lucivan Barros. I'm the Senior Application Scientist at Thermo Fisher Scientific. One of my jobs is to manage the application lab in Boston area. It's 35 minutes from Boston. There we do some trainings, some trials for customers. We do some workshops, which by the way, in June, we're gonna have a material characterization workshop, which is free. So I'm just inviting everybody, if you can, you just come, it's free, you don't have to pay anything. So in this presentation, I'm gonna be talking about technological advances. So basically it's to complement Professor Ubink lectures, but it's gonna be more focused on what we have here in Cal Poly, more focused on the process 11 on our instruments. Most of the experiments, I'm gonna show a lot of videos here. Most of these experiments were done by Dr. Valerie Stahl. She is the application specialist for food extrusion, so she knows everything about food extrusion. I'm the senior application scientist for extrusion, basically for material science. All right, so let's move forward. This is the agenda for this presentation. I'm gonna start just giving a brief background, talking about the demand, price, expectation. I'm gonna explain why we use extrusion process for food application. And then I'm gonna talk about feeding systems. What do we use for feed materials into the extruder? What are the main challenges and how can we prepare better the material to better feed them into the extruder? And then I'm gonna go to the extrusion, screw design, process condition influence, and at the end I'm gonna show the difference between the die for high moisture meat analog and for low moisture meat analog. So it's gonna be a lot of videos. Hope you guys enjoy. So let's talk about plant-based meats. I always like to start my presentation with some questions. So I brought here some questions. We don't have to answer, it's just for thinking and reflect, okay? So how many of us have noticed plant-based meat alternative while you're doing grocery shopping? Well, I bet everybody here have seen a lot of different varieties of plant-based meat analogs on the shelves. And this question is very important because it's gonna tell us about the demand. The demand is increasing immensely, which means a lot of people nowadays are more concerned about getting more sustainable food, sustainable product. And this picture, actually my fiance sent me yesterday, is a real picture. So you see that they have a whole area for plant-based meat analog. And then I zoom in here. There's beefy taquitos, meatless chicken nuggets, burger made of, they call beefy burger, but it's meatless, right? So these just tell us the increase of the demand. The second question is, how many of us actually have purchased one of these instruments? So in my case, I've seen more than I've bought, actually. And these tell us about the price. So unfortunately, these products, they are still being sold at a higher price compared to the meat. So, and this Professor Zhao, she showed some survey yesterday. So people are still not ready to pay high costs for this kind of product. And this brings me to the next question. Finally, for those who have tried, did you like it? And most important, do you keep buying? How do you have we introduced these products in our daily meals? Have we replaced our eggs, our bacon, our sausage in the morning by plant-based meat, analog sausage? So, and this question tell us about the expectation, our expectation as a consumer for this product. So I was talking to Professor Bilal yesterday, and food is life, food is culture. So if these products are not reaching our expectation, we're not gonna buy. And that's the main goal here. The main goal is that the first buyers, they keep buying this product. So we have a lot of challenges to face. And how can we solve this challenge? We need a continuous production to attend the increase in demand. We also need this process to be scalable to decrease the price of retail. And also we need a process that is flexible enough to give us the flexibility to tailor texture, to tailor taste, because if the material doesn't look appealing to me, if I don't like the color, if I don't like the smell, I'm not gonna buy it. Maybe I'll buy it first, I'll try it, and I'm never buying again. And how can we achieve all of this? If you're thinking in twin screw extruder, you are right. So continuous process using twin screw extrusion provide us a fast, cost-effective, and more reproducible process for food application. So since extrusion is continuous and is scalable, we can decrease the cost of production, which will be reflected to the retail price. Also, since Professor Ubik said, we have a high range of adjustable process parameters. So we have a lot of variables that we can play around. And with this, we have a great flexibility to tailor the product texture. So by changing one variable in the extrusion process, you can vary a lot the texture. And we saw yesterday by changing the temperature, by changing the water content of the high moisture meat analog. And this is an example right here. We have here the same material, exactly the same material processed with the same machine, but we change one variable that I'm gonna tell later. And then we see that the texture is completely different. Here we have fibers, longitudinal. Here we have parabolic fibers. Okay, but not everything is great. With high flexibility, we make these more complex as well, especially for protein extrusion formation. You know better than me that the mechanism for this structure is very complex and not very well understood yet. So, and also it differs from different protein sources. And I just find out as well that the same protein source cultivated in different regions of the planet, they have a different structure. And this is translated in processability. So the way you process a pea protein cultivated in here, and the other one cultivated in, I don't know, Brazil, the processability of these two proteins is gonna be different, even though they are the same protein. So that's very interesting. Which means that we still require intensive product development, intensive research. That's why having a small extruder is very important, because we can use 1-2 pounds and achieve and change a lot of variables, and we have a lot of information from this. Since the available material, we don't have a lot of material available to do research. Okay, even though extrusion still offers great potential for production innovation. Okay, process design for plant-based meat analog. When we do process design, we are worried about achieving certain properties in the final product, right? Properties in the final product. For example, texture, the fiber length, the strength of the material, the firmness of the material as well. And this is not only for plant-based. This is also for licorice, puffed snacks, all of the food application. And these properties are going to be influenced by several factors. And one of the factors is the material itself. So how much water you add, what's the protein content, what's the quality of the protein, the source of the protein, also what is the source of the non-protein components that you are mixing with the protein, starch, fat, oil, and etc. And obviously this is going to be also influenced by the extrusion process. So all the process parameters, screw speed that you use, the temperature profile, the feed rates that you are feeding the materials in it will have great influence on those properties right there. Instrument specification, if you have a high volume machine, if you have a high torque machine, and the dies. What kind of dies are you using? Are you using a cooled slit die? Are you using a short die? Are you cutting? So you have different properties in your final product. And as we already know, because we've been talking about that since yesterday, we have two types of meat analog, plant-based meat analog, high moisture meat analog, and low moisture meat analog. We know the products, we know the typical application, and we're going to introduce also the setup. So it's basically, we have two setups for low and high. We have the twin screw extruder, which is it's going to be the cooking pot, where we vary all the process parameters. We set the process parameters and we can vary the process parameter. We have the feeding, so we feed vegetable protein, we feed water, we can feed oil and other components. And then for high moisture, we have the cooled slit die. We have a die adapter and the cooled slit die. And then for TVP or low moisture meat analog, we have a short die and the cutter. We don't necessarily need the cutter, but helps. Okay, focusing on the high moisture meat analog, basically we have two main characteristics that we know by now, right? We have high water contents during extrusion, and we use the cooled slit die. And with that, we can achieve this muscle meat-like texture. So basically, we have the extruder here. We feed material in the hopper. The screws will convey this material, mix, cook. We add water at some point, and the material reaches the die where all the texture is done. So this is a profile of temperature. So we go in a very low temperature, it's blue. We increase the temperature up to the die adapter, and then we cool down for the structuring, the texturing of the meat analog. Yeah, so in the screw section, we have the protein, the denaturation, and all the cross-linking. Basically, we're cooking inside the extruder. And in the die section, we have the shear-induced structuring, which is giving the material the texture. What do we have here? Critical control points for HMMA. So we have feeding systems, we have the extrusion itself, and then we have the die, which for HMMA is the cooled slit die. For TVP, it's going to be the short die. So basically, the feed system that I'm going to talk about feeding solution, material preparation, and extrusion. I'm going to talk about screw design, unit operation, and process condition. They're going to be the same for HMMA and LMMA. Okay, let's moving forward. Feeding systems. For feed, the material that we feed, they are powders, right? So for powders, we recommend twin screw feeders. And for food application, we recommend gravimetric. Yesterday, Professor Ubink already mentioned the difference between gravimetric and volumetric feeders. So gravimetric is basically a feeder on top of a scale, so it's more precise, more accurate. So what is a feeder, right? We have the funnel hopper, which is a big hopper on top of here, that I put this picture right here. So this is the reservoir, right, to put material in there. We have an agitated hopper. The agitated hopper will prevent bridge building. So you see this is an agitator that rotates and all the powder that is here can be mixed and be able to be fed with the screws, which is the last thing and most important. We have the feed screws and the outlet tube. These varies in geometry, size, diameter, if it's coiled or concave, and this is related to what kind of feed rate you want to achieve and what kind of properties your materials have. Feeding is the key for continuous extrusion process, which means that if you don't feed consistently, your final material will not be consistent either, right? So when you have your material, you have to do some observations, like is my powder too fine? I have irregular particle size and shape. Does my material flow? Is it sticky and oily? Yesterday we were grabbing the protein powder and it was all over. So it's very sticky and in my hand I had to wash. So in all of these will introduce some challenge in feeding, because all of these materials, all of these characteristics makes the material to be more challenging to feed. For example, the material can build bridge. What is that? So basically, this is the agitator. The feeder is open right here. This is the agitator inside the feeder. And then you see that this material just won't flow. And if you have that, we're going to have irregular powder feeding, which means, again, if you have irregular feeding of your material, you will have irregular final product, irregular quality in the final product. Electrostatic charging. A lot of materials, they have a lot of statics which blocks the extruder funnel. So the static goes here and you basically block it, so you're not feeding anything more. So that's a challenge. And compacting of powder in feed screw channel, it's basically you block some powders, they are very easy to compact. Yes?
Someone advised us to use wax, coat it with a wax. Yes.
Wax?
Wax.
Oh, wax, okay. To add in the material?
Yes, not to the material, to the surface of the internal surface of the feeder.
But you might contaminate your material, right?
I mean, it's a food grade.
Okay.
It's recommended to just. What do you think?
Yeah, I will recommend another solution in the next slides.
Okay, I'll wait until
yeah, okay, so you don't have powder discharge, so we cannot feed what you. Yeah, I was saying that the powder, sometimes if you press the powder, it compacts very easy. So during the rotation of the screw, you have the powder being compacted, and you block the funnel. Sorry, the outlet tubing. Okay, let's look at some solutions. For example, here, for irregular powder feeding, we can prepare these materials previously. For example, we can mix some very, if your material is very challenging, you can mix with other kinds of proteins or other ingredients, such as fibers, to enhance the flow of this material. Another thing that you can do is preconditioning. Precondition, as Professor Ubink mentioned before, we add some water to reduce stickiness, avoid the bridge building and charging in these materials. In this video, oops, 1 second. Okay, here's a video comparing no preconditioning and with preconditioning. You can see that here we have some material slipping here and not a lot of material being fed consistently. And here you see after preconditioning you have a very good flow of material being fed. Electrostatic charging, so that's the solution that I recommend to ionize the airs with the use of this ionizer we call ionizator. It's basically you feed on top of the feeder and then you get rid of the static that is built with the powder. So this is with the ionization. We see that there's no building up of material around the tube. But without the ionization, little by little, you see increasing the material here, and at some point, this will be so big that it's gonna affect the feeding rate. So you don't have a very consistent feed rate. So this is with ionization. So you see that all the material is getting inside this container, but without the ionization, you start seeing material being dropped away out of the container. That means that my composition will not be consistent.
Where can I find the ionization in my device upstairs?
Carolina?
Oh, I don't have. I need to buy it. Okay, makes sense.
You already have a book for it.
Yeah. Okay, so ionizer mounted on feed funnel of the extruder reduces the statics and avoids blockage of the extruder feed funnel. We also have force feeding options. Sometimes the material is so light, so the bulk density is so low that the gravity is not enough to put the material inside the extruder, so we need to force this feeding. So it's basically a screw that rotates and pushes the material directly into the screw of the extruder. So we feed the force feeder, and the force feeder just pushes. So you control the feed rate with this guy, with the twin screw feeder that you guys have upstairs, and the force feeder just push down.
Can we use it for emulsion, like very low viscosity?
Low viscosity?
Liquid, like similar liquid. Can we use the force feeders?
No, we recommend the peristaltic pump.
A side pump.
Yeah.
Is it
A peristaltic
available
pump.
for? Oh,
Yeah, just like the one that you
The
have,
one
but we
for-
changed the tubing.
can handle higher viscosity than water.
Yeah, it depends on the viscosity, but yes.
So emulsion, suspension can be
Yeah.
handled.
Yeah. Okay. Another thing that I wanted to show you is this twin screw granulation. What is that? Twin screw granulation is a wet extrusion, which is basically done in a room temperature or 30 degrees C. So you can see that this is blue. We add the material, we add water, and we don't have a die, we have an open discharge. Sometimes we can use special discharge screw elements that they look like a pineapple, just to break down the granules. So this is very useful for pharmaceutical application, basically to increase the flowability of very challenging powders. So you transform the powders that is sticky and doesn't flow into granules that you can easily handle. So there are some benefits. We have mixed ingredient uniformly, so we ensure that we have a even distribution of powder, liquids, and other additives. We can control moisture level by adding more or less water. And this is very important for the texturing for food application. We improve the flow properties, which I already mentioned, and we enhance the product stability by just keeping the consistency of the particle size and shape. I'm gonna show here, okay, so before, we have, so the product quality depends on how the granule quality is, so the particle size, if it's regular, the density, the shape, and the structure, and all of these, the granules properties will be changed by the process parameter. So screw speed will have an effect, throughput, the liquid and solid ratio, the screw configuration, all of these factors will have a different effect on what you're getting at the end of the extruder.
Was the water content they use for the granulation?
It depends, can be 10%, can be 15, can be...
But not very high. It should
No.
be less than 20.
Yes, it's slow because you just wanna make granules. This is not a process, this is a preconditioning. Actually, that's a good point. Yesterday, Professor Ulrika I'm referring to your talk a lot because it's just to complement, yeah. And we have the preconditioning for big extruders to do the preconditioning and then add this material into the extruder. But here with the process 11, you can use the same instrument for both process. You remember when we turn it on the extruder, we have the options between HME, hot melt extrusion, and TSG, twin screw granulation. So you basically select what kind of process you want to do it.
The screw profile will be same, or is it
The screw profile is a little bit longer because it sticks out of the extruder and it's gonna break the granules. I'm gonna show a video in the next slide, this one.
You mentioned pharmaceutical companies have a lot of applications.
Yes, they use a lot because it helps to make the tablets, to compact those tablets that we.
I know of them based in California.
So wet granulation of protein powders using the process 11 hygienic. This is the process 11 hygienic. We have the mini twin here, the gravimetric feeder, water pump, and this is the granulation setup. We have the container and we have a protection because, as I said, the screw is sticking out of the extruder, so it's dangerous for you to cut yourself if you touch. Everything is controlled. We saw that yesterday. Everything is controlled through the HMI. So here they are feeding this protein. They did not specify what kind of protein is that. And then you cannot see very well, but you add water and then you break up into granules the material that is being extruded. There it is. So you see it's kind of like a pineapple. We call this one distributive mixing elements. And this is the difference before the granulation. It doesn't flow very well, and after granulation it flows much easier, so you can use that to produce your product. So because it's easier to feed, you're going to have a more consistent feeding and more consistent quality in your final product. But these help us to handle this material, but also influence the quality of the final product. For example, here we have a very irregular shapes and irregular size before the granulation. And here, after we granulated at 30 degrees C with 10% of water, he's busy. And then we have the difference in the SEM images, right? Now we have big granules with regular sizes. Here we have a very small, fine particle with different sizes and shapes. And these influence the final product. Here we have a very rubbery high moisture meat analog, but here you start to get better texture. So the granulation process will help in the final product as well. All right, so this was for the feeding system. Do you have any question about feeding system and all the challenges that I showed? I'm gonna move forward to the extrusion part. So screw design, the unit operations and the process conditions, which happens inside the extruder. Okay, as we saw today in the morning, the first lecture of the day, there's a wide variety of process parameters in the extrusion process. We have independent parameters, we have dependent parameters. We also have in the independent parameters, we have the direct and the step ones. The direct is the one that you can change right away in real time. And the step is the one that you have to stop the extruder and change the thing and then restarts the extrusion process. For example, the screw configuration, you cannot change during extrusion. You have to stop, disassemble, and assemble it again. But it still is an independent parameters because you have control of that. The dependent parameters, they are response to the independent parameters. So all the torque, the pressure that Professor Umbenk mentioned, mechanical power, specific energy, all of these is just a response for what you're changing in here. And I wanted to start with the screw geometry. So screw geometry is one independent parameter and affects basically everything that you see here. So the screws are the heart of the extruder, so it will affect the pressure, torque, the degree of filling of material inside the extruder, shear rate, residence time distribution, melt temperature, flow type if it's shear, flow, extensional flow, and most important, the material flow. For example, here we have a twin screw extruder. We have material being fed here. And a twin screw extruder works in starve-fed mode. What is that? It means that the barrel channel where you have the screws, they are not fully filled with material in the whole length. So we have this graph right here with filling degree. So in the conveying elements, we have about 30% of material filling up that cavity. So we feed material here. This material is transported at 30% of the degree of filling. Once it reaches close to a mixing zone like this, for example, if you remember the mixing zone, they don't have a very conveying power, right? They need to build up pressure and to push the material through them. So when the material reaches here, this is not conveying very efficiently, so the material starts to accumulate in the beginning of the mixing zone. And once it accumulates, the pressure goes up, and the pressure will push the material through the first mixing zone. And then once the material reaches here, the end of the mixing zone, you have more conveying, so you push this material at a lower degree of filling. And this is going to happen for each of the mixing zones in the screw profile, which will result in change in the pressure. So if you have here no fully filled, you have low pressure. Depending on the configuration of the mixing zone, you have higher pressure or lower pressure, higher pressure, and the highest pressure would be at the die because you're basically pushing a lot of material into a little hole or a little slit. So we have non-pressurized regions, pressurized regions, and so on. And we use these characteristics from twin screw extruder to give us more flexibility. So we use these non-pressurized regions to feed a second material, to do venting, to add liquid like water for plant-based meat analog, and also to collect material as well if you need. And luckily, as we know already, these screws, they are segmented, so you have a lot of flexibility, so you can build your screw based on what you want to achieve with them. So here I have some very nice screw elements that were 3D printed. So if you want to pass, those are mixing, no, those are conveying, those are mixing. And then as Professor Mick showed, we basically build a screw configuration based on what you want to achieve, right? So we have conveying elements, just very quickly. It's for transportation of material. They are self-wiping geometry. And as I said, they are only partial filled. We have long helix that I showed yesterday for group 1, I believe. Then we have a standard helix and short helix to increase the pressure, compress very low bulk density material. And I brought here a real example. So we had this customer, Carolina and I, actually, we had this customer that they want to blend powders, but one of the powders were very sensitive to shear because it was causing fibrillation. So we basically built a screw only with conveying elements. Question? Question?
Interesting.
Yeah.
Question, like, okay, because I have the same issue.
So we have here long helix. We put two powder. We fed two powders here with long helix, so we can intake this material, and then we convey these materials, and then we feed the third material in here. I added more long helix conveying elements here too, and then we have basically everything conveying elements. And then I use the twin screw granulation. You can see here, it looks like a spike pineapple to mix these powders together. So, just a spoiler, it was not very effective in mixing because they are not mixing elements, they are conveying elements. But we could optimize by add some of these elements throughout the screws and very mild mixing zones as well.
Those conveying elements, do they have a different depth? Because I feel some of them really not that deep, so they cannot hold the powders and convey, especially fine powders. Do you have different?
Not different depth, but different distance between the
So
flights.
you have the first one, which is not self-cleaning, you know, the...
No, it is. This one, yes.
Oh,
This one is the
so
long
not
helix.
the one we have, like the first two, which is...
Not this one.
Not this one.
Yeah, this is the wide throat element, and this is the regular conveying element. So in this case, we have with different pitches, right? The long helix, the standard, which is 1 L/D, and this very short one to increase pressure and compress the material.
So which one can handle fine powders for us in future to work with?
No, they all can handle, but to feed, you should use this one, the long helix, which is the one that you're using.
The one you saw yesterday?
The long helix, not the wide throat.
No, those are no good.
Yeah. Those are for other kinds of material. Okay. Then we have the mixing elements. They apply mixing. So they used to introduce shear energy to the extrudate. They apply dispersive and distributive mixing. Well, what is the difference between these two different kinds of mixing? I'll tell you. So imagine that we have a mixture of two materials. Material A, material B is the dispersed phase, material A is the matrix. And if we apply distributive mixing, we basically split and recombine, split and recombine. So we distribute the material B throughout the material A. So you have a nice distribution throughout the material. If we want to do dispersive mixing, is a different thing. So now, to disperse, we apply deformation. So we elongate, we extend, and then up to a certain deformation, and then we break down these big droplets into smaller droplets. So you have a more dispersed material. Here we have a more distributive material. But the ideal is to achieve both of them, right? So you want your material to be very well distributed and very well dispersed. So if you're adding some additive into food, some flavors, you want them to be very well dispersed and distributed throughout your food. It's like when you put salt, you want in your food, you want to mix because you want the taste to be well mixed and taste good throughout the food, not only in one bite. And we can do that with extruders because they are excellent mixers and they can apply levels of distributive and levels of dispersive mixing thanks to these screws, the co-rotating, intermeshing, self-cleaning screws. So basically what happens is that the material is wiped from one channel to the other channel, and this creates a lot of mixing. So you are basically splitting material and recombining because they are moving from one channel, the extruder is like in this direction, from one channel to the other. And how exactly the distributive and the dispersive mixing happens into the screw. So basically we have the mixing elements, right? For distributive mixing, we normally use this, they are narrow. And as I said before, it's through melt division. So you split and recombine. So imagine that the melt, the material is right here. And once this is rotating, the material slips through the sides. So you are splitting the melt. If the material creates like a pool of material here, this material don't have enough time to go through the sides. So this material is squeezed between the tip of the element and the barrel wall. So that's how we apply dispersive and distributive mixing with the screws. Any question? And yeah, and yesterday, I don't know if you remember, Jared, we were talking about staggering in a different angle, and then I mentioned like, why would you do like not staggered, like 0 degree? Remember that I asked that? And then I told you that I would tell you, and you never asked me back. So sometimes you wanna make this part wider to apply more extensional mixing, more elongational mixing, more distributive mixing. Okay. All right, so by doing that, by doing the offsets that I just mentioned in different degrees, we can control the amount of shear that is being applied to the melt. The residence time can be changed. The conveying power, the pressure, the torque. So you can control a lot of things just by changing how these materials are, how these elements are staggered. And this is just like a summary of the different degree offset in the mixing zone that we have in our screw here at Cal Poly. So at 30 degree, the conveying conveys material, 60 as well, but 90 degree, there's no conveying at all. So, which means that we have the highest shear being applied to the melt. And also the residence time is longer. The pressure is higher, the torque is higher. So, screw configuration influence dependent parameters. Question?
Yeah. We are food scientists. We ask by our managers, we want to create a product, and they give us ingredients.
Yeah.
Have different moisture, we do a preconditioning, and it has different particle size. And I'm responsible to build that profile to have a good product. What should I look, what is the standard? What 3 steps I do and I'm done? I have the best selection between 30, 60, 90. How do I make my decision?
We do have recommendations, obviously. We have a standard screw for different applications. But at the end of the day, if that screw works well for you, you can make some adjustments. But at the end of the day, it's more about trial. So sometimes some screws won't work well for your material. For example, if you have food application, they are thermosensitive, so you don't want a screw that applies a long residence time because you don't want to keep the material inside the extruder exposed to high temperature and exposed to high shear for longer. So you will change your profile of the screws to apply shorter residence time. That's one example. If we have very shear sensitive materials, so you don't want a very aggressive mixing zones because I don't want to break up my fibers. I want to ensure that I have fibers in my material. So these will be too aggressive for fibers that are sensitive for shear, for example. Then I'll go to 60 to 30 degree. If I need to increase my residence time, as Professor Ubik said, we can add the reverse elements at the end of this mixing zone. So that's how you do your research.
So is the trial and error, there's no software or AI that helps me based on my particle size, my
Oh,
moisture
there
content
are-
that tells me this is the best profile.
Yeah, there are a lot of
Decision making, not
There-
I make the decision.
There are a lot of studies that use simulations right now, but this is a science that is increasing right now. For example, for polymer, we have some standards for different kind of application.
And of course that goes more complex if I'm using the 11 millimeter. It's easy to do this.
What do
If
you
I
mean?
want to scale, I mean it's easy because it's a smaller scale, but if I want to scale it up to 125 millimeter, what are the challenges with the profile?
Yeah, that's why you need a
'Cause
lab
everything will
scale
change.
machine. You need a lab scale machine, so you figure it out, your process conditions, you develop your process, and once you have this figured out, you can build a 250 millimeter twin screw extruder screw profiler. Because you don't want to keep changing. one mix element is like, I don't even know, heavy.
But also the large extruders, sometimes they don't set it like segmented, they can have like so many.
Yes.
Yes, correct.
That's why you need to do it like in a snarl and then you scale up each
Okay, moving forward. Segmented screw design to combine the unit operation. So this is just to illustrate the feeding of powders and the extruder. So we have the protein-based ingredient being fed in the funnel. We have high volume conveying elements. We have the addition of oil and water. They can be added in the same place. They can be added in different places as well. We have standard conveying elements, mixing elements, reverse conveying elements, and these, as Professor Belard just said before my talk, we need to think that as a huge and expensive cooking pot. So basically we have this addition of material at lower temperature. So you put your powder, you put your water below 100 degrees C, and then we have the cooking zone where we heat over 100, and then we start applying mixing, we start applying aggressive shear to be able to cook this material, to be able to allow the molecular structure of the material to change and the rheological properties as well. And here is an experiment that they open the barrel just to see how it looks inside. So we have here in the first powder and water feeding. We basically have still dried material with some water, with some hydrated. And then we have a mixing zone. We have a dough mixing and conveying. So here we have water being mixed with the powder. So we have a dough. And then the cooking part, we have some burning. But the cooking part, we apply shear, we cook, we have higher temperature, and it's here that the molecular structure are changing of the protein. We're good with the extrusion part, the barrel, the screws. Cool. So now let's talk about the cold slit die for high moisture meat analog. So we have a modular cooled slit die. So it's basically we have a top and bottom half. That's the die. We have the die adapter. We can add a breaker plate that will change the flow profile inside the slit channel. And then we have modules that we can make it longer, shorter, depends on the protein, the need of the protein. We also have on top some ports to put some probes, for example, FTIR, Raman spectroscopy, pressure, temperature, if you want to monitor other kinds of parameters. And we basically need to consider three things in a cold slit die: the die entrance, the length, and the temperature difference between the adapter and the cooling die. So the entrance is we can add some breaker plates to change the flow profile of this material. For example, here we have two breaker plates, one with 37 holes and one with 14 holes. and they will change the velocity profile, will change the flow profile of the material that is entering the slit, will orient the fibers longitudinal to the flow. So if you guys want to pass along. The length also plays an important role here. It's basically adds residence time, so adds how much longer the material will stay inside this slit. If the material needs a lot of time to produce this texture, you need a longer die than other materials. So it's very material dependent. And the heat transfer, we have modular, so we can, this is one module. We can add a second module, so we can run water at one temperature here and water in the other, with other temperatures in the second one. So we can play with the heat transfer.
Those are for analytical tools. I can do inline.
Yes.
Can I do injection?
Theoretically, yes, but practically no, because imagine you have the, we don't have mixing here. If you add it,
if I coat it like that. Oh.
If you what?
Inject something to coat it.
To coat.
Coating, yeah. It's like I'm injecting, you know, a layer of maybe some fatty material that coats the flavor encapsulated or something in
no, I understand. Yeah, it is a possibility. You can use these parts to inject, but depending on the pressure, you're gonna have material coming out. So you have to inject something pressurized. Force injection. Yeah. And also you need to see if you will be able to coat the whole area, right? Because you are injecting from the top. What about the bottom? Maybe we need a longer die, so the material goes and keep going, and this coating.
Which brings us back to the same point that Dr. Jobing mentioned. It's better to inject with the last segment in the extruder, where you still can mix the material.
Yeah.
And that's your best
Not
option.
here.
No, here is too hot.
Here.
Yeah.
Actually.
So the last part.
Yeah, the last part, because you need to mix. Unless you want to do coating, but yeah. Coating, there is a technology for coating which is co-extrusion. So you basically have a die with two extruders feeding material. So one extruder is feeding the coating and the other extruder is feeding the core. And then you have material coated. We do offer that, by the way, but that's another thing to consider. Yes.
The breaker plates, are there breaker plates in all of these, or do you only use those if you're trying to slow the flow?
Yeah, if you want to change the flow, you use this.
Okay.
You don't have to.
And that's
we
just
didn't use yesterday.
slow it down, not to give it texture.
No, it's to change the flow profile, which will change the texture. So it's not to slow down, it's basically to change the texture. Imagine that the material is passing through these 14 holes, and then this will align the fiber in one direction.
Okay.
I'm gonna explain a little bit more in these slides right here. So this is the slit die. So basically what we have here is a parabolic flow profile, which means that this is a picture after we break on the longitudinal direction, and you can see this parabolic structure as well. If we add a breaker plate like this one, now we have this kind of flow. So we have orientation, a longitudinal orientation of the flow. So this will change the structure of the final product. Now we have fibers aligned in the direction of the extrusion process.
It's like a die within a die.
Yeah. It's just like a modification of the die entrance. Yes.
Question there. Do you have any idea of the degree of anisotropy differences between running it with and without breaker plate?
Yes, we're gonna show some SEM images that is gonna show a little bit about this.
Okay.
Yeah,
Because I'm assuming it impacts anisotropy.
it does, definitely. So this is two videos showing the difference in the texture. This is without the breaker plate, and this is with the breaker plate. So we have more fibrous material here.
And we were not
More
using
like-
the breaker plate yesterday. right?
We did not.
Okay.
We did not. So you tear more longitudinally in the longitudinal direction of the strands.
I hope we still have ours. We didn't use it. Did we throw it away? No.
Another thing is the die length and feed rate as well. So here we have extrusion of pea protein isolate with 55% of water. Here we have the 18 centimeter die. Well, media not found. Okay, it's okay. It's not in my computer. Yeah, let's see. Do we have internet in this computer? No. I'm gonna send this presentation to you guys, and then I'm just gonna explain. So this length was not enough to process this material. It needs more time, so we basically have some material, water is splashing from here. That's the video. And here we increase to 36 millimeter. You see that we have one module, two modules, three modules, and then we have more stability in these strands. And you might ask, what is this black part coming in here? So here we will measuring the residence time of the extruder. So basically, and based on different throughputs. So basically, residence time, how do we measure residence time? Do you guys have any idea? Huh? Yeah, we basically inject a dye or a second material that is different from the material that you are processing. And then we basically time how much longer we see that material coming out. So residence time throughput influence the residence time. So higher throughput from 2 to 5 kilograms, you have a lower residence time, a shorter residence time, and also impacts the distribution and homogeneity of the material. So this video will show a little bit of that. Unfortunately, media is not found. I don't know. Okay, in a shorter die, here we have two different materials with a 27 centimeter and 36 centimeter. This is the visual evaluation. So shorter die shows sample with less regular texture, and longer die seems to give more homogeneous texture in the final product. And we can see that with the SEM image that I mentioned, Professor Ubik. With a longer die, we still see this flow profile, this parabolic flow profile in a very regular way. It's very well distributed. Here, we don't see very clearly the parabolic flows. You see more like a turbulent flow with a shorter die. And not only the length of the die, but the temperature between the cooling die, right here, is like 50 degrees C, and the die adapter. So we did the test with 100, 130, and 150, the temperature of the die adapter, and then you can see this difference very clearly in the SEM images, which is translated into the texture, as you can see down there. So remarkable effect on the flow profile, and with thus we have the influence on the texture. This is a video of HMMA process with a twin screw extruder 24 millimeter. That's the pilot scale that we have. Is a much bigger instrument than the process 11. So we have a gravimetric twin screw feeder here, feeding pea protein at 50%, and the water is going to be 50%, so 50-50. We have the peristaltic pump feeding in the third port. So all of these ports we can use to collect material, to add more material, to put probes, FTIR, Raman spectroscopy probes, to monitor these properties in real time. We need a chiller to provide cooling. And just like the process 11, the TSC 24 has the same HME, so it's very easy for you if you buy a 24. You don't have to be trained in the 24 because it's basically the same control, the same display. Everything is basically the same. And then we can see the trends, the process trends, the process parameters trends, the temperature profile, everything is there. The overview of the feeder. We do the calibration of the gravimetric feeders through the HMI. I think we did yesterday with group 1. And then we have the modular cold sled die. Another chiller for the die. And that it is. 4 kilograms per hour, extruded at 400 RPM. And let's see the texture. Yummy. And then they're gonna increase the temperature barrel for around 155. And let's see the effect on the temperature that we actually saw yesterday a little bit, but now for me that looks more appealing. So by changing the temperature, you greatly changed the texture. Look at that. And that's the serving suggestions. That looks good.
Is this the 16 or the 24?
The 24.
24.
The 24.
How big is the slit?
24 millimeter.
So 11 is 11. The slit.
Oh, the slit. That's a good question. I don't remember. I'll check. Yeah. Okay, so that was for high moisture meat analog. Let's talk a little bit about low moisture meat analog, which is also called TVP. The setup, we use the same instrument, same temperature profile, higher temperature, but in the screw section we have the same thing happening, right? The protein, the naturation, the cross-linking is happening. And in the short die, we have the expansion and the shear induced structure, and then we cut. So low moisture meat analog, we use lower water contents. We use the short die, and this is an intermediate product. So to achieve this meat-like texture, we need to rehydrate this product. Yes, as I said, we use the short die nozzle, and things that are very here the expansion is going to happen, and it's very dependent on the pressure and the die entrance as well. So we need to be able to have a pressure drop here. So as Professor Bick already mentioned, we have high temperature, higher pressure here, and once the water comes out, the water will evaporate because the pressure is much lower outside. And here I explain the steps that happens in the expansion. So first, we have all the mixing, all the cooking, all the gelatinizing, water mix inside the barrel, and then the pressure drop happens in the short die, which is we have the flash, evaporation. Then this bubble will grow, will make the strand to expand, and 4, we have some shrinkage of this material, especially for protein-based material. This is a video of the process of expansion. This is for starch in the process 11. So we basically have a nozzle with a hole, and you see that you have the expansion, all the bubbles growing, and the material solidifies, and then we have this material which is used to manufacture puffed snacks.
This dye is not for expansion. We have another one.
Yes,
So
you
we
have the
still can
best.
use the milks for the, 'cause this is
Yes, yeah. You have the best one, the designed for that. This we still have a flow that goes this way, but yours is better. Avoids there's low volume in yours to avoid burning material. So, but you still can use this. And since we talk about starch, there are some differences. Who asked? I think it was you, right? The difference between the expansion behavior for starch-based and protein-based. But there are some differences, but there are some similarities as well. For example, the bubble nucleation starts in the extruded die, both. We have a higher expansion ratio for this one, lower expansion ratio for this one, and here we have shrinkage of this material. Let's see if the video works. So that's the difference between, you have a much higher expansion ratio there, and here you can see that the difference between the hole and the strand is not much, but here we have a huge expansion of this material.
Do you know what that is?
This is pre-protein, I guess. Pre-protein. Here. Pre-protein. Moving forward, the length of the die also plays an important role in the expansion as well. Let me play these videos. So we try different lengths. So here 16 millimeter is the one that we have here. And these are longer, 40 millimeter, 4 centimeter. And here we just have different water contents. So this is for 33% at different lengths of the die. And you can see that longer the die, higher the expansion of this material, and less is shrinkage. At some point, if you add more water, you don't have much difference. And with lower water, you don't have much difference between the longer dies. But you have to find the sweet spot to have this difference. I like the sound of this video. It likes fireworks. Okay. The process. Production of texturized vegetable protein by twin screw extrusion in that process 11. We have here the process 11 hygienic. We have a volumetric mini twin. We have 2 peristaltic pumps adding 2 different liquids and the face cut pelletizer. We saw that already. Everything is integrated. You can control. You can also control you can see the feeder here, but you can also control the liquid pumps here too. Liquid feeder for water and vegetable oil. And this is a mixture of wheat gluten, soy protein, and corn starch. feeding the mixture. And this die has 3 holes. You can see. And we have a lot of expansion here because we also have, it's not only protein. We have some starch added to the material. That's Valerie, my colleague. So the face cut pelletizer cuts the strands on the face of the extruder. This material, you drop this material and then you cool down by blowing air. Let's show. So you cut it here, the material drops here. There are some air blowing here, and then goes to a cyclone, which rotates to finish cooling. It's gonna show.
That's on the 11?
That's on the 11.
Well, you can have all these accessories on the 11.
Yes.
And you can actually package it from here.
Do
That's just to finish up the
yeah, this is the
not to
cooling.
dry
Yeah,
it.
that's to cool down the
It's
material.
not to dry it, further dry it, like finish it up.
Yeah, you can dry.
So it's not to cool it down, it's to dry it, further dry it, after leaving the extruder.
After the extruder, yeah. To cool.
And that face cut with the pipe and everything.
And she's doing the rehydration. Say that again, I'm sorry. Sample after rehydration.
Those accessories fits for 11, 16, 24 is the same or is different sizes? Or is the same?
It's the same
accessory?
size. Same
Same
size.
size.
Just the adapter is different.
It's different.
Because it needs to be adapted. Yeah. But the 16 and the 24 is powered by the extruder, and for the 11 is powered on the wall. That's why I mentioned that I only have the face cut for the 16 because it's powered on the 16. I cannot use in the unless I have a 16 next to the 11, so I can power from the 16. And there you go. You see the fibers with a high magnification on SEM. Cool. Other applications, animal or pet food. This is a nice application. This, we not only do human food, but we do pet food. And this is dry animal feed with insect protein. That's very nice because we have the whole system, right? The process 16 in this case, peristaltic pump, gravimetric feeding. We are feeding 2 materials simultaneously in the same port. And this, look at this. Mealworm, larvae.
That would have been powdered already.
And then the starch on the top. Come on, guys. It's protein. So you see, feeder 1, feeder 2, liquid feeding, everything is controlled through the HMI. And here we have some issues, like 50% of the mealworm, there's a lot of fat, so it's not good. What they did was increase the starch percentage. Nice video to watch before lunch. But I'm not ending with this video, so it's fine. So this is for pet food. We have the face cut pelletizer here again. Obviously, if you increase the speed of cutting, you have smaller pellets. Pellets are dried in a cyclone and are collected. There you go. Cool. And this is the last video, I guess. It's just another example for low moisture meat analog. using the 16. That's the 16 with the strain nozzle. We have water feeding. So this is what we're gonna do today. We have always like a powder feeding system. So this is the recipe. We always have a feeding for powder, then water. Everything, they went high temperature in this case. %30 of liquid feeding, and this is the outcome.
This is the 16.
16.
Yeah. The early of the video, the flights, the first flights, the early flights is totally different.
They use this.
So, yeah, but it's bigger. The
Yeah.
depth.
Yeah.
So they can convey. Those for the 11 is not deep enough.
Correct. Correct. And then you do the rehydration, and then you can use that in sauces or burger patties. Great. Okay, take-home messages for HMMA and LMMA. Reliable powder feed is very important for the process, as I mentioned before. If you don't feed consistently, the final material will not have a high quality. You should take advantage of the segmented screw design to adapt all the units operations inside the barrel. And you can use different dies. You can change the die entrance in the cold slit die. You can you can play with the heat transfer, the pressure that you are adding, that you're not adding, the pressure that is happening inside the die. You can change the process parameters, and then we can see what's going to happen with the final product. So this is the conclusion of this presentation. But I also brought here some nice literature that I've read. We have 4 literature. These I found very interesting. They adapted this die to be both a cooled die and also expansion, and they form these different kinds of morphology. It's nice if you have interest in reading. I put the DOI here. That's all for today. Thank you so much, and we can have some questions.
Thank you so much. Thank you. That was really inspiring. And unfortunately, none of the literature is citing me and Dr. Yoko. So that's something we can discuss later.
Next time I know what to do.
I think we have 5 minutes for any Q&A. If you have questions for Lucivan.
Question?
You said you could program the water pump rate on the screen.
You can control it, just like an on and off.
Oh.
Sorry. Everything is integrated, but can be better. Anything else?
You mentioned that feed rate is important for consistency. Let's say, hypothetically, the feed rate stops, right? And so then that creates almost a void in the barrel. So then, because of that void, we have nothing but water.
Yes.
And then we start the feed rate again.
Mm-hmm.
That would then lead to build up in the mixer, or
Build up. Normally, you're gonna have a void, as you said, more water than powder, which might be bad because the water is gonna be very hot, and this is gonna kind of like splash in the die. So you need to avoid that. Hypothetically,
Yeah.
If
now we're done.
it's not, never happens.
Any other questions? Lucivan will be here whole day we will have the hands-on, and tomorrow is joining us for the cooking session. Because you want to see some of the products that Processor 11 can produce and how we can use them in cultural cooking.
All right. Thank you.
Extrude the mealworm?
If you want. No.
Yeah, as we see from the presentation, extruder is so powerful. Actually, we're getting to learn that extruders have been used in pharmaceutical, it's been used in batteries industries, they've been used in car industries, EVs industries, and a lot of the chips are actually nowadays extruded. So I don't want to delay you. We're keeping you away from the lunch, which is very delicious today. We have some tofu, so plant-based, and we have some other things. Enjoy your lunch. We will have a break from 12 to 1, and we start our hands-on sessions at 1, and we will go back to the groups. I will remind you. Do I need to remind you your groups, or you have the 3 group leaders here, so find out your groups, and yeah, we start at 1. Enjoy your lunch. Thank you so much.
You remember your group?